everyone again. So, the work that I'm going to present you today is about a novel hybrid continuous multiscale model for the efficient crack propagation analysis in generally anisotropic microstructures. I would like to thank my co-authors, Professor Fabrizio Greco and Paolo Lonetti, and Doctors Domenico Ammendolea and Arturo Pascuzzo. So, let's start with the motivation of this work. It is well-known classical bulk homogenization approach, so classical multiscale model based on a first-order bulk homogenization scheme are no longer valid for softening microstructure materials, since an objective overall constitutive responses are found for different sizes of the representative volume element, as is clearly shown in this picture. So different overall responses for different sizes. And so, therefore, in the literature, there were proposed more refined approaches in order to overcome limitation of classical first-order bulk homogenization schemes. The main advantage is that injection, somehow, the injection of a macrostructural size in the homogenized behavior. This allows the problem to be proposed. I just like to recall some of these refined approaches. Let's say, the higher order homogenization, or an enriched continuous homogenization as the micropolar ones, and finally the so-called hybrid discontinuous homogenization schemes, which is the topic of this presentation. But most of existing continuous discontinuous homogenization approaches are established in a F-square-like approach. So generally, they are characterized by a huge computational curve. So in the present work, we propose a more efficient continuous discontinuous multiscale strategy for the efficient numerical simulation of crack propagation in periodic anisotropic composites. So let's go more in depth in this method. The present continuous discontinuous multiscale approach is intended to be applied in combination with a diffuse interface modeling approach at the macroscopic scale. What does it mean? Such a diffuse interface modeling approach is based on the so-called cohesive Lonetti finite element method, which is used to simulate multiple cracking along non-prescribed paths. Such a method is essentially relies on the insertion of zero thickness interfaces into the discretized domain, and all these interfaces are potential crack trajectories. In particular, the interface the embedded interface are cohesive interfaces, which possess general mix and mode anisotropic fraction separation law. Anisotropic, it means that the PSL, the fraction separation law, depends on the orientation of the macroscopic graph. On the other hand, the bulk elements possess a general nonlinear behavior, such elastic damage behavior and anisotropic version. So the main assumption of the model are 2D periodic microstructure, well-separated spatial scales, quasi-static loading and small deformations, a general nonlinear behavior of the constituents at the microscopic scale, so the scale of the microstructure. Conversely, at the macroscopic scale, we consider a homogenized damage model up to strain localization, for the bulk elements at the macroscopic scale, and the homogenized crease load for the embedded interface to be homogenized. So after the strain localization occurs. So that's why we call this approach a hybrid continuous discontinuous multiscale model. So for bulk homogenization, the micro to macro relation to obtain the macroscopic, the overall constitutive behavior in the nonlinear range are rather well established. So there exists some very known formulas, but there are no analogous relations uniquely defined for obtaining the micro to macro link for the crease representative unit cell, the repeating unit cell, here used for homogenization purposes. So the formula for the macrotraction follow a natural definition which is obtained by enforcing equilibrium at the macroscopic interfaces, but there are no unique definition for the macro separation in the literature. In this work, this macroscopic separation, that is the displacement jump for the macroscopic graph, can be related to the discontinuous part of the macroscopic strain derived from homogenization. And this discontinuous part of the macroscopic strain is linked to the total macroscopic strain, which can be derived by usual nonlinear homogenization by using the regularized strong discontinuity kinematics introduced by Oliver and simply sketched in this slide. So just we can link the discontinuous part of the microstrain to the macroscopic displacement jump of the interface. Let's see more in depth this link. This link is make it possible by enforcing a kind of sort of equivalence in terms of dissipated energy between the cohesive repeating unit cell adopted for homogenization purposes. You can see the discontinuous part of the macroscopic strain. I see the equivalence between the cohesive repeating unit cell and the equivalent macro graph. You can see the overall displacement jump for embedded interfaces. And this equivalence is possible by after introducing a characteristic length scale indicated with H, which is simply the ratio of the unit cell area to the macroscopic graph. The macroscopic length can be estimated from the RUC geometry, the repeating unit cell geometry, by using the approximative formula proposed by Turkotov. So let's go to the computational implementation of the proposal. So the first step, the first stage is the so-called offline stage. It is a simulation stage which concern only the microscopic scale, that is the repeating unit cell of our periodic medium. So the first step of this stage is the parameterization of the macroscopic space using spherical coordinates in this way. Then the discretization of the entire macroscopic space adopted, which is useful for the subsequent computations. That is identification of a finite number of radial macroscopic path directions, and then the derivation of the macroscopic strain database by subjecting the same RV to the previously identified macrostrain path direction. Then the interpolation of the previous strain database, and finally the detection of the stable part of the response by performing a rigorous localization analysis, which is based on the singularity condition of the so-called naturalistic tensor. This allows to split our response into a stable part, which will be used in the bulk, and in the unstable part, the softening part, which is used to drive the interface behavior at the microscopic scale. So this is the second stage of the method, that is the online stage, which concerns the interface behavior. This is an online stage because it is performed during the simulation of the macroscopic domain, macroscopic problem. So the input is the microscopic displacement jumps, then the computation of the discontinuous microstrand using this formula, then the computation of the average continuous microstrand as the average between the two adjacent flow elements to the generic interface, then the determination of the macrostress on the calculated microscopic stress strain base, and then the computation of the macroscopic fraction. It's important that the continuous part of the macrostrand is not microscopically derived, but is extracted on the fly during the microscopic scale simulation. The two main advantages are no need for additional easy repeating unit cell computation, that means higher computation efficiency, and not explicit derivation of an approximate fraction separation law, which means higher computational higher numerical accuracy. So let's go to the main numerical example used to validate the proposed numerical procedure. The first example is based on this microstructure, that is a porous microstructure materials with rearranged holes in a rectangular array. This is the cell, the square cell used for our nonlinear homogenization purposes. Here, the nonlinear characteristic of the matrix, which is assumed to be damageable according to an isotropic model in a local damage model. You can see just an example, the main overall responses in terms of stress strain for different macrostrand paths involving compression, tension, also shear deformation of the unit cell. And then we go to the main numerical simulation, that is the so-called multiscale numerical simulation, MNS, which is performed on our macroscopic problem. In this case, we study a simple 3-point bending test on this perforated beam, and we go, the aim is to validate the procedure by means of a suitable comparison with a fully meshed model, that is with a so-called direct numerical simulation in which all the microstructural details are represented explicitly in the problem. So, homogenized versus fully meshed. The load displacement curve are superposed to each other with very small error of the peak, less than 1%. But the most important thing that we reach a very high speed up value. So an analysis, multiscale analysis, which is faster, 40 times faster than the direct numerical simulation. Also, the crack party is captured by our approach for mode 1 propagation. In order to better validate the model, we propose a comparison between different meshes, a random mesh and a mapped mesh. The results are in agreement with each other, and they both are in agreement with a reference analysis in which only a single interface is introduced in the model due to the symmetry condition of the test. So, very, very good results in mode 1 crack propagation. Let's go to the second example, which is now about inspired microstructural material, in particular a nacre-like microstructural material with a brick-and-mortar arrangement, which confer to this microstructure a higher fracture toughness due to the possibility of the crack to go through the reinforcing plates. So, same thing. We studied two cases, a mode 1 loading and a mixed mode loading. So, for mode 1 loading, These are the results. Also in this case, very, very small error on the peak, less than 1%, and very high values of the speed up, 80, faster analysis. And here, a mixed mode body, the same test, but with the crack. Also in this case, the MNS and the DMS predict the same result. Also, in terms of global crack path, you can see the Greco numerical simulation, the path is this one, multiple cracking. Here, just the main crack predicted with the same angle. And the speed up value is even higher, 130. So we are rather satisfied by our results, which encourage us to continue with this way, propose more efficient multiscale model. So, in conclusion, a novel hierarchical multiscale model is proposed for periodic microstructures, in particular for transparent composite, based on the synergy between continuous discontinuous homogenization approach and the diffuse interface model. An efficient computational strategy is proposed to compute on the fly the overall fraction separation law, starting from the macroscopic sensitive interfaces. The main advantage of the proposed model is to solve completely a nonlinear two-scale problem at the cost of a single-scale problem. The proposed approach has been fully validated by different Just, I would like to trace some future perspective for this work. First of all, the extension to the setting of large deformation. This could allow us to better study the influence of the interaction between fracture phenomena and instability phenomena in more complex microstructure, more complex inspired composites like nacre, which are the main of the present. Thank you for your attention.